Welcome. This lesson is on electric field strength of a point charge in free space, which is a subtopic of electric forces due to point charges in Unit 18 electric fields. By the end of this lesson, you should be able to recall and use E equal to Q over 4 pi epsilon 0 times R square for the electric field strength due to a point charge in free space. Understand that, for a point outside a spherical conductor, the charge on the sphere may be considered to be a point charge at its center. Coulomb's law can be used to find how the electric field strength varies with distance for a point charge. Imagine a point charge positive Q producing an electric field around it in free space. A positive test charge small q is placed at a distance r from the point charge Q. The electric force that acts on the test charge is F. Based on the definition of the electric field strength at the point is given by E equal to F over Q. Apply Coulomb's law, the magnitude of the electric force F equal to kQ over R square. Simplify the equation, we get the magnitude of the electric field strength of a point charge, E equal to K times Q over R square, where K is the Coulomb constant, which is equal to 1 over 4 pi epsilon 0. Electric field strength is a vector, so the resultant electric field strength at a point due to two or more point charges is the vector sum of the electric fields due to each charge. For a charged conducting sphere, when the charge distribution is fixed, charges will lie on the surface of a conducting sphere uniformly. So, there is no movement of charges in the charged conducting sphere, and the resultant force on charges in the conducting sphere is zero. Hence, the electric field strength is zero in a charged conducting sphere. The charges at the surface of a conducting sphere are equally spaced. And all the field lines at the surface of the sphere are at 90 degrees to it. So, the electric field lines are radial and appear the same as that of the point charge, originates from the center of the sphere. Consider a charged conducting sphere with positive charge Q producing an electric field around it. Next, plot the electric field strength of the sphere versus the distance from the center of the sphere. The distance from the center of the sphere to the surface is the radius, capital R. We have learned previously that inside a charged conducting sphere, the electric field strength is zero. Outside the sphere, the electric field is the same as the electric field originating from a point charge with the same amount of charge at the center of the sphere. Then, we can get the electric field strength at the surface of the conducting sphere, K times Q, over capital R square. The electric field outside a charged conducting sphere obeys the inverse square law, which means that the electric field strength is inversely proportional to the square of the distance from the center of the sphere. For example, when the distance from the center of the sphere is doubled, the electric field strength will decrease by a factor of 4. Let's try some examples. Please pause the video to try the question. In this question, two identical positive point charges are positioned at the fixed points x and y. The electric field radiates away from a positive point charge. So, at point A, the direction of the electric field due to the point charge at x is to the right. And the direction of the electric field due to the point charge at y is to the left. Assuming rightward is positive, so the electric field Ex is positive. And the electric field Ey is negative. The resultant electric field at point A is the vector sum of the electric fields Ex and Ey. Recall that the magnitude of the electric field strength of a point charge is given by E equal to kQ over R square. Then, we apply the formula. Rx is the distance from point A to the point charge at x, which is 2.5 centimeters. Ry is the distance from point A to the point charge at y, which is 10 minus 2.5 centimeters, and equal to 7.5 centimeters. It's given in the question, the resultant electric field strength at point A is 4.1 times 10 to the power of negative 5 Newton per meter. Convert the unit of Rx and Ry from centimeter to meter and substitute the values into the equation. Simplify the equation and solve for the charge Q, which is 3.2 times 10 to the power of negative 18 Coulomb. We have come to the end of this lesson.